In this video, we're going to look at another type of convergence test known as a ratio test. Let summation a sub n be an infinite series and L is equal to limit as n approaches infinity absolute value of a sub n plus 1 divided by a sub n. Number 1, if the limit as n approaches infinity absolute value of a sub n plus 1 divided by a sub n is equal to L and this ratio is less than 1, then the series summation n equals 1 to infinity a sub n is absolutely convergent by the ratio test. Case number 2. If the limit as n approaches infinity, absolute value of a sub n plus 1 divided by a sub n is equal to L larger than 1, or limit as n approaches infinity, absolute value of a sub n plus 1 divided by a sub n is equal to infinity, then a series summation n equals 1 to infinity a sub n is divergent by the ratio test. Number 3. If the limit as n approaches infinity, absolute value of a sub n plus 1 divided by a sub n is equal to 1, then the ratio test is inconclusive. That means we can't apply the ratio test to determine the convergence or divergence of the series. We have to apply another test. So the series may be convergent or divergent. So there are 3 cases. Either ratio L, the ratio of the successive terms, is less than 1, then that means the series is absolutely convergent by the ratio test. If the ratio of the successive terms is L bigger than 1, or the limit is infinity, then the series is divergent by the ratio test. And if the limit is equal to 1, the ratio test is inconclusive. We have to apply another test. So let's look at an outline of the proof of the ratio test. So here we have the limit as n approaches infinity of a sub n plus 1 divided by a sub n is equal to L. Now for large n, absolute value of a n plus 1 is approximately equal to L times absolute value of a sub n. Similarly, absolute value of a sub n plus 2 is approximately equal to L times absolute value of a sub n plus 1. But absolute value of a sub n plus 1 is equal to L times absolute value of a sub n. So this will give us L times L absolute value of a sub n, and this is equal to L squared. L squared absolute value of a sub n. And similarly, absolute value of a sub n plus 3 is approximately equal to L times absolute value of a sub n plus 2, which is equal to L squared times absolute value of a sub n. And simplify this, we get L cubed. So we can see the pattern. Alright, so the infinite tail of the series summation an, it behaves like absolute value of a sub n plus absolute value of a sub n plus 1 plus absolute value of a sub n plus 2 plus absolute value of a sub n plus 3. We're going to look at the infinite tail of a series because the infinite tail of any series tells you whether it converges or diverges. Now, we have absolute value of a sub n plus absolute value of a sub n plus 1. This is approximately equal to L times absolute value of a sub n. Absolute value of a sub n plus 2 is equal to approximately equal to L squared absolute value of a sub n. And absolute value of a sub n plus 3 is approximately equal to L cubed absolute value of a sub n, and so on. Now let's factorize absolute value of a sub n times 1 plus L squared plus L cubed plus L to the 4th, and so on. So we can see that this part is a geometric series with common ratio L. So what we have is absolute value of a sub n times 1 plus L squared plus L cubed plus L to the 4th, and so on. And this is a geometric series with common ratio L, and we know that a geometric series converges if L is less than or equal to 1, if L is less than 1, strictly less than 1, and larger or equal to 0, converges. And if L is bigger than 1, diverges. The geometric series diverges. But this is the same conclusion as a ratio test. So this is kind of the outline of the proof. It's not a rigorous proof. If you want to look at a rigorous proof, you can look at basically any standard calculus textbook will go through all the details of a proof. But this just gives you the big picture, the big picture behind how the ratio test works. So let's look at the summary. The ratio test is asking, does the tail end of the series summation n equals 1 to infinity a sub n behave like a geometric series, and if the common ratio L of successive terms, limit n approaches infinity, absolute value of a sub n plus 1 divided by a sub n is equal to L less than 1, then the series converges absolutely. Alright, let's look at an example. Here we have test the series summation n equals 1 to infinity minus 1 to the power of n times n squared divided by 2 to the n for convergence. Let's apply the ratio test with a sub n, is equal to negative 1 to the power of n times n squared divided by 2 to the power of n. L is equal to limit as n approaches infinity, absolute value of a sub n plus 1 divided by a sub n. This is equal to absolute value of negative 1 to the power of, plug in n plus 1 wherever we see an n. So negative 1 to the n plus 1, n plus 1 squared divided by 2 to the power of n plus 1 divided by the original fraction divided by negative 1 to the power of n times n squared divided by 2 to the power of n. So L is equal to limit as n approaches infinity. Let's simplify this. We get absolute value of negative 1 to the n plus 1 divided by negative 1 to the power of n times the remaining parts, which are all positive, so we don't need to apply absolute value to the remaining parts of this fraction. N plus 1 squared divided by n squared times 2 to the n, flipping this fraction, 2 to the n divided by 2 to the n plus 1. Alright, so we get L is equal to limit as n approaches infinity, subtracting off the exponents here, we get negative 1 to the power of n plus 1 divided by negative 1 to the power of n, subtracting exponents, we get negative 1 to the power of n plus 1 minus 1, so we just get negative 1 times, and simplifying this part, we can rewrite this as n plus 1 divided by n all squared, and this part subtracting off the exponents, so this part reduces to 1 divided by 2 to the n plus 1 minus n, the n's cancel out, we get 1/2. Now if we take the limit as n approaches infinity, we're going to get, this part is just going to give us 1, because we divide by the highest power, and that gives us 1. So absolute value of negative 1, this is 1 times 1/2, which is less than 1. Now let me just talk about this limit y is 1. Just expand on this. Limit n approaches infinity. So dividing through, we get n over n, which is 1 plus 1 over n, all squared. And 1 over n, this ratio approaches 0 as n approaches infinity, 1 over a large number. So we get 1 plus 0 squared. This is equal to 1. All right, so the ratio is equal to 1/2. Since L is equal to 1/2, and this ratio is less than 1, then the original series, the given series, summation n equals 1 to infinity minus 1 to the power of n times n squared divided by 2 to the n converges absolutely by the ratio test. Converges absolutely by the ratio test. All right, thanks.